Hello all. In this video, we're going to take a very brief look at two closely related computer vision tasks that have similarities both in what they're doing, but also in the kinds of deep learning models that we might use to solve them. So we're going to talk about object detection, and we're going to talk about image segmentation. And for each of those, I'm going to introduce, just in a very hand-wavy way, one example of a model that can be used to do this task. These are much more specialized models. Like most convolutional neural networks that are used for something like classification, they may have variations, but for the most part, they look pretty much the same. That is not the case with object detection. People have found success with a variety of different approaches to the problem. They are all involving more specialized layers than just a CNN, but they do in fact use some of the same layers that a CNN might use. So we are going to focus in this video on the YOLO model. I'm going to show you a diagram of YOLO version 11, and we'll just kind of talk through what it does, and we'll look at examples of object detection and image segmentation so you understand what it is that we're trying to do with these models. We'll talk a little bit about data sets as well, because that's one of the issues with this as a task is that it is just incredibly time consuming to build models to do this task. All right, let's take a look. So this is from some readings that I've written up for my students. I will note that I'm not going to go through all of the text here. I'm going to say a lot of the things that are written in the text. So this is an example. I grabbed a random image off of the internet and I ran it through a pre-trained model of YOLO, which is the object detection model that we're looking at. This is actually YOLO version 11 and the smallest of those models. So the goal of this model, it is pre-trained on a data set called COCO. Common Objects in Context. That's what COCO stands for. This is almost a benchmark data set for object detection. It's like what everyone wants to train their model on to show how well it works, because it has lots of everyday objects, not just like things on a table, but things you would have in your home, things you might see out on the street. So it identifies a lot of different classes. There's a lot of, I'll go over the details of COCO later. And so here the model is attempting to make sense of this scene that it's got. You can see there's 1, 2, 3 that are labeled in blue. There's 1, 2, 3 light green. There's 1 dark green. So it's found quite a few objects that it thinks it recognizes. What we're seeing is the plot function that the Ultralytics YOLO implementation includes. This draws the objects that it's found along with their categories and the confidence of the model in its categorization. So the goal of object detection is to find objects in images and to put a bounding rectangle around them, a bounding box. So that's what's being drawn here. So for this item in the front, you can see that it's drawn a green box that encloses that entire food item. It isn't enclosing the plate, so it's specifically about the item on the plate. And then it has labeled that food item and given a confidence value. So 0.75 is not a super high confidence, which is good because this is not a pizza. But you can see why the model would list it as pizza. I don't know quite what other word it would use. There probably doesn't have anything that is going to be equally good. It does pretty well. This glass behind is probably not technically a wine glass, but it's similar. It has identified here a bottle. It's got, I think, another bottle also in the same space. So it's seeing the mustard bottle that's behind the ketchup bottle and marking it, I think, as a bottle. And then it also has marked a salt shaker as a bottle, which, it probably doesn't have salt shaker as one of its categories. So that's probably as good as it's going to get. We have one really large blue bounding box that encompasses, I believe, the table. So maybe you can't quite see it because it's written over, but it might say dining table or something like that. At least it's something having to do with dining. So it's got that. And then it has a small bounding box at the back that again we can't quite see with this view of it. I'm not sure if there's actually a person there or if it's incorrect. It's hard to tell, but it's not very confident. Notice the low confidence values that some of these have, while others it's much more confident in. So when you run one of these models, you get a list of, or a set of different lists out. You get a list of bounding boxes, and then corresponding to each bounding box, you also get a list of the category labels that it's assigned to each object, and you get a list with the confidences. So this captures all of that information in one place, but it's actually pretty easy in the code to get that information yourself. So if you're trying to identify pictures that have wine glasses in them, for instance, then you can look at the data that's come out of this, look for any objects that have that wine glass as a category, and you could even make a threshold so you don't consider something that it's identified that has a lower confidence than say 0.5. So there are ways that you could actually use the outputs of this model really easily. Okay, I want to talk a little bit about the architecture. It's not my goal that you fully understand the architecture. There's a lot here. I will actually, in the description of this video, I'm going to add some of the links because a lot of the architecture pictures that I'm going to do in this video and the next one, I've drawn from sources, and they're actually really good tutorial sources that you should go and look at to understand better how some of these architectures work, if that's what you're interested in. So there usually are, within object detection models, you still need to do that kind of feature detection that we talked about with image classification. So there are usually sections of the models that look like a CNN featured finding part, that first big section of the CNN models that we talked about before. All right, so I had to make this really small. It's a little hard to see. I apologize for that. You can find the larger version of this in the source paper, which I will cite. And also, if you just do a search for YOLO V8 architectures, there's dozens of variations on these. I picked this one because I thought it was relatively straightforward to understand. So you can see here, the first thing to notice is that YOLO as a model tends to have three sections. It has what they call the backbone, it has the neck, and it has the head. And they have different purposes. So the backbone is where the input starts. So if you follow the path here, the input starts and it flows downward. And some of what's happening here is similar to the kinds of things that we would do with our convolutional feature finding. In earlier versions of YOLO, the backbone was often just the feature finding part of a standard convolutional neural network, where it would do convolutions and pooling and convolutions and pooling. Here you can see the pooling has been replaced by another kind of unit. You can look up the details. It's a special set of layers that go together and do some processing that is not quite the same as just pooling. But fundamentally, we're doing the same kind of feature finding throughout the backbone. And there's some scaling that happens because that's important. What you see is that several different points in this process produce data that flows into the neck. The purpose of the neck is to resize these features that have been found at the smaller scale. So you notice it's doing upsampling and concatenating together data and upsampling and concatenating data again. So it's doing a certain amount of convolutional processing, but it's also just sticking together the results that were found at different scales. And then we go through another phase of feature finding, and we have three different levels, probably of size perhaps, that feed into the head portion. The head is where these models might differ from each other. As an object detection model, the head is going to produce the bounding boxes and the categorization. When you have an image segmentation model, in addition to producing the bounding boxes and the categorization and the confidence, it also produces the image segmentation mask, or I call it a map typically because it's not quite a mask. But that's the ultimate layer is much like with the CNN, we have that layer at the end that does the categorization. Here, the head is the thing that actually decides what are these objects, and it produces the actual bounding boxes that are the output. Now, with many of these object detection models, there is some kind of a hard limit on how many different bounding boxes you can find in an image. Some of the earlier models had quite strict limits. Maybe they could only find 4 objects in an image. These days that's much less the case, but there probably still is a maximum number that is possible, just based on how the models typically work. Unless they are producing the bounding boxes in some sort of sequence over time, then that might possibly allow it to produce an unlimited number. All right, so I mentioned this before. I mentioned image segmentation. Let's talk a little bit about it again. So an image, a segmentation of an image is where we mark every pixel in the image according to what object it belongs to. So if it doesn't belong to any object, it's marked as a background pixel. And otherwise, it is marked not just as, we don't just make a black and white mask. You could have a segmentation system that does that. It only finds one object and it marks it in white and everything else is in black. But more typically, especially with this kind of a system, we have different values that are associated with each object that's detected. So for instance, you might take the index, the classification code, and use that value to paint each pixel that belongs to that object. So if there's a clock in your picture, then every pixel that's part of the clock will be given the number that represents the category clock. So the output you get from an image segmenter is a picture, a mask, or a map, the same size as the input, where every pixel tells you what object it belongs to. With YOLO, along with the models themselves, we have, as I said before, these functions that plot the results. And so the image segmenter does that as well. So I'll show you the result of running the image segmenter on this picture. This is like 3 dogs up on a rocky cliff overlooking a beautiful valley. And you can see that it has identified the 3 dogs. It gives us the bounding box and the category and the confidence just as it would if it were just doing object detection. But in this case, it also tints each one with a color that corresponds to the category. So if you remember, even in the earlier picture, the different bounding boxes had different colors. Those colors corresponded roughly to the category that each belonged to. We're doing the same thing here. The bounding boxes are drawn in a color, and the actual pixels are tinted with that color as well. That's something that's done in the process of producing this image. The output segmentation mask is probably more simple than that, but this is something that actually even a beginner could do. You could write the code to do this plotting. It's not that hard. I also want to point out one other thing. So you might notice here we have these 2 dogs, and they're quite accurate. It's missing just a little bit of the toe of one of the dogs, which I'm going to scroll this up so you can maybe see the bottom of the picture. Yeah, so you can see the toe here is missing. This might be the dog's other foot that it hasn't quite gotten. There's a foot down here that's missing. But by and large, it does a very good job of capturing these 2 dogs. It does the same. I'm scroll it back down. It does the same with this dog on the other side, but you might notice that the color of the dog is different. Why is that? Well, if you notice, there actually are 2 bounding boxes here. It has identified this object as 2 different things, and it's reporting them both to us. We could decide which one we want. I suspect it may be the case that the other one has the higher confidence, or maybe it's just done in order. I don't know. You probably couldn't guess because you can't read it here, but that's why I wrote code that prints out those things. Otherwise, it actually is confused here and thinks that that dog might possibly be a horse instead. Right. These systems are not perfect. They're never going to be perfect. Humans aren't perfect. We're still significantly better than these. But if you imagine having a conversation with a 3-year-old or a 4-year-old about the objects that you see in a picture, that's kind of the level of accuracy that I tend to see in these. So image segmentation lets us do lots of really interesting things, from cutting objects out of a picture to cropping around just an object, to telling perhaps how two objects are interacting with each other based on their proximity to each other. It's a really, really interesting component, and it's a really interesting task to take a look at. All right, let's talk about data sets. So in order to train YOLO, it had to be trained on a data set. And I want you to think about the details of that data set and the scale of it. And then think about what it would take to build your own data set if you wanted one. So these YOLO models were trained on the COCO data set. This is, as I said earlier, one of the classic data sets, almost a benchmark. Almost every model has a pre-training out there somewhere that is in fact on this COCO data set. So the COCO data set has over 300,000 images in it. For object detection and segmentation, that's a lot. But it's not that large in comparison to things like ImageNet, which might have even many more. So as I think it was 330,000, but I just put over 300,000 here. Each image has potentially multiple objects in it. So if you count up all the objects across those 300,000 images, you get about 1.5 million annotated objects. That's a lot. That's what, about 5 per image on average? So each object is assigned to one of 80 object categories, and it also includes 5 captions, 5 different captions that describe the scene. So they have text descriptions of each scene, and 200,000 of the images are annotated. So we have 300,000 images. They're not fully annotated. Probably the test part of it is not. So 200,000 actually have the bounding boxes, the categories, and the segmentation maps, all of those created. Now, what does it take to create one of these data sets? I want you to think about that. When we do image classification, one of the things that we often do with image classification when we want to make a data set is we go collect a bunch of pictures, and then we sort through them, and we sort them into different folders. So all the pictures of frogs go in folder 1, and all the pictures of lizards go in folder 2, all the pictures of fish go in folder 3. It's not a simple task, and you want it to be done accurately, but it's a doable task. We need much more specific information if we want to do object detection or image segmentation. Some human, needs to go through the data and annotate each and every object by hand. You have to define the bounding box. You have to write down the category for every object in every image. If you're doing image segmentation, it's even more than that. You have to paint the pixels that belong to that object and not the ones that don't. So again, it's a lot of work. This is supervised learning. There are definitely people interested in automating some of this or semi-automating it, or doing semi-supervised learning where we only have to mark some of the objects and then it sort of figures out what we're doing. And I will say that I wrote this down at the bottom here. There are online tools that are pretty good where you can start annotating and it will automatically try to figure out what you're annotating, and it will propose annotations for you that you can modify or delete or accept. So this is people know that this is a hard part of this task. Building a new data set is just an almost ridiculous amount of work. In my own research, I work with image classification for the most part, and it takes us weeks to prepare the data set, weeks of collecting images and then organizing them into categories and so forth. It's a long process. To do annotated images like this, where we're annotating the objects within them, would take us even longer. It can take months. So it's a constraint on this kind of problem that the data is difficult to build. One of the benefits that, say, large language models have is that they are self-supervised in some sense. Like the targets that need to be fed into the system are an intrinsic part of the data itself. So you collect up lots and lots of text, and then you just hand it all over to the LLM and it goes with it, and you don't have to spend time hand annotating the text. Now, some of that does happen, even in things like large language models. Among other things, they want to do some quality control on the text and make sure that the text is actually not not going to be nonsense. All right, so we're not going to get into the gory details here of how these object detection models work. If you want more information, I'm going to leave some links, as I said, in the description for this video. There are also links in the readings that I'm posting as well, so that you can find some additional information and learn how these models work. I do want you to realize, though, that they are not hard to work with, assuming you have the data set. The data set is the hardest piece. Once you have the data set, actually taking a model and training it can be really simple. In a later video, I'm going to show an activity I'm preparing for my class where you will walk through and use and then train a YOLO model and see how it does. It's pretty fun, and it's remarkably straightforward. I will stop there, and I will see you very soon.